Hi class, today we're going to be discussing modeling geometry and polarity. There will be 3 videos to this. That's very different than the other labs. This one I'm just going to go straight through the lab itself. Part A and C are very, somewhat mostly easy. Part B goes, going to need more information. So instead of having a super long lecture, I'm breaking it up. I'm only going to go through what you need to know about how to do the lab here. And then my next video will be more in depth strictly for part B. My third video is how to put Lewis structures together. It works well for some. I will cover that in that video, what it works with and what it doesn't. And it's not something I created, it's something I found, but textbooks don't seem to cover how to put Lewis structures together the way that I do. And my way is, to me, is fairly simple. Again, doesn't work 100%, but it's certainly better than struggling staring at things. Okay, so part A is pretty simple. You're going to have 4 pictures, and you see one's an ionic compound, the others are covalently bonded, nonmetals. And you can see here that obviously you can see that one is colored, some things are, you're going to have to record 2 to 3 physical properties. So one is what do you see based on these pictures, and knowing your information, you should already have covered beginning in the text what physical properties to ionic compounds and covalently bonded or nonmetals. You should be able to come up with 2 more or at least 1 more physical property. I have done some work and have been a little nice. I've separated these out. You should definitely know the physical characteristics of these compounds. Now, the next thing you're going to have to do is sodium chloride. There's a picture you're going to be given, and you're going to be asked to discuss it on a microscopic level. Microscopic means not what we can see, but what we cannot see with our eye. So what we have discovered is with sodium chloride, there's a lattice structure. Lattice structure means it's very neat, very organized pattern of opposite charges. These opposite charges keep this very, very tightly bound and very hard to have a high boiling point and a very high melting point. If you take one chloride, for instance, let's take this one. You see it's surrounded by 4, there's more. I'm looking at it as a flat surface here, but there's 4 sodium ions, and if we look at a chloride, you can see, there's a chloride, and if we look at it, there are 4 sodium atoms around it. And then if you look at a sodium, you have 4 chlorides. Now again, I'm looking at it flat. There's actually 6 because you should have one behind and one in front of us, but we're not looking at it as a 3D structure. Okay, so because of this, that means ionic compounds have very high melting points and very high boiling points. Ionic compounds also tend to be polar. They will interact with a polar molecule, and they're solids at room temperature. Okay, so now this is part B. We're going to get into Lewis structures. By now you should have been familiar somewhat with Lewis structures, and hopefully you've tried to draw them out. You will definitely have to do this whether you want to or not, because you're going to have to start thinking of these compounds in 3D to see everything in pharmaceuticals. Everything that we do is based on how they look, because we need to know how compounds come together. One compound might be too big to interact with another one. So these are very important things, even if it doesn't seem like that to you. I work in a lab. When we were doing certain things at a certain time, I don't want to just being very vague, but we had to make sure that these compounds would interact, and one of the things was look at it as draw it out, look at the 3D, and then expand on that to make sure that we were doing everything we can to make sure that these compounds react, to get the reaction we wanted. Okay, so we're looking at covalently bonded compounds. Let's look at HCl. HCl, hydrogen has 1, chloride has 7, and when we come together, that means that hydrogen will have a duet, chloride will have an octet, and we draw the lone pairs out. So the lone pairs here count 2 electrons count for 1 lone pair. So we have 3 lone pairs on the chloride, and then we have 1 bond, which is equal to 2 electrons. So we draw it as a dash because it's a lot cleaner to look at when we do dashes. You should know that a single bond has 2 shared electrons, which means 1 shared pair. Double bond has 4 shared electrons, which is 2 shared pair. And triple bonds is 6 shared electrons, which is 3 shared pair. All right, so let's break down what we understand here. We're looking at hydrogen cyanide. There's 10 valence electrons. This fills an octet for carbon and nitrogen and a duet for hydrogen. So because the lone pair is still counted for the nitrogen, and if you count that, all of their that around it is an octet. Carbon has its octet. It's good. Now we're going to start looking more and more at the center atoms on our compounds to do part B. So if we look at carbon, it has everything it needs to fill out an octet. Now the new words you're going to use is electron groups. Electron groups is a group of electrons that can be single bond, double bond, or triple bond, or a lone pair. We count it all as one. It doesn't matter if it's a single bond, double bond, or triple bond. It's one. So we count it, think of it as an attachment. We don't care what type of attachment or what type of interaction, it's still one. So if we look at hydrogen cyanide and we look at the center atom, this is all focused on the center atom. This has two attachments. We do not care what type of bonds these are. It's just got a bond. It's got an attachment and interaction to it. So here's a little, I put together how to determine it. But if we look at this compound, it doesn't necessarily always say center atom, but it's always directed at a center atom. Then we do this. We do not care about the ends. And in this one has two electron groups attached to the carbon atom. So part B, you're going to be given 3 different sections with different molecules for each, some ions, and you're going to be asked to fill out steric number, electron geometry, number of bonding electron groups, number of lone pair, molecular geometry, how many bonds how many bonds have a dipole? I must have cut something off there. I don't know. Oh, how many bonds have a dipole? So do the bonds have a dipole? If present, do the dipoles cancel out each other? And is this molecule polar? So this is some of the things I'm going to cover in the next lecture. You're going to be asked to draw all these compounds out. So make sure that you are comfortable. This is good practice in order to do this. Now, this is a definitions page. I've put this together to help you if you need to look at how to understand these. Steric number is the same as electron groups. We're looking at the center atom and how many attachments are around that center atom. So if we will look at this one again, steric number and electron group number are 2. There's 2 attachments around it. So that's not very difficult to understand. I'm going to start covering more of these later. But number of bonded electron groups. So if we look at this one, again, it's 2. We don't care that this is a triple bond. We don't care that this is a single bond. Bonded groups, for this case, means attachments as well. So we have 2 groups that are attached because a triple bond is still a group. We're not looking at individual what it is. We're just looking at the attachments. So number of bonded groups is 2, and there are no lone pairs on it. Okay, so let's continue on. So here's a little bit more information. You're going to have 3 different sections, and each section you're going to have to upload your drawings. I want complete Lewis structures. It should be clear. If it's not legible, I will not give you credit for it, and my say is the end of it, because just because you can make a sense of it doesn't mean I will, and I'm not going to argue about that. You will get credit or no credit. Make sure it's legible. You can take a picture or scan each section. If you have an iPhone, there's a scan option under notes. If you have a problem uploading to LabFlow, you can send it to my school email. It has to be submitted before the due date and time, and I will go by whatever the time and date it says received by me. And no credit will be given if that is past it. I do not care. I will go by the black and white on that email, and that's not debatable as well. Make sure you upload to the correct section. If I can't find it and it's not under the correct section, it's marked wrong, because I'm not going to be searching for your work as if I'm supposed to know that you put it all together in part 1. Okay, then we get to a next section here, this drawing 2D molecules. Your PDF discusses drawing these in 2D molecules. I'm not going to expect you to do this. This is something that I don't even think should be in this lab. I get what they're trying to do, but this is very hard to do online. So you can skip this part. Don't worry about it. Now, part C, again, not too bad. This is actually a fun lab to do. Sometimes some of these labs, it's too bad that we're not in person to do, because they really are interesting to see something that we really never think about. You're going to be given this picture. Now let's go through this picture. You have oil and water. Oil is a lot lighter. It's less dense than water, so it'll sit on. This is why when there's an oil spill in the ocean, the oil will sit on top of the water and suffocate everything. So this is, unfortunately, but this is why oil will sit on water. It's less dense. Water is heavier. Now, what you're going to get is you're going to have to determine which one of these is polar and which one is not polar. And these are your experiments. You're going to be dealing with polar and non-polar substances. Polar and non-polar do not want to be near each other. Have you ever had salad dressing and shaken it up and it will always separate? That's because no matter how vigorous you shake it, you're dealing with polar and non-polar, and they will always separate out of each other. They will not stay. And if you put a polar substance in a solution of water and oil, that polar substance will go straight to whatever's polar and stay away from the non-polar. If you put a non-polar into a substance of polar and non-polar, it will go straight to the non-polar and stay away from the polar. So that's what you're going to see here. You're going to look at this and you're going to compare each one with a blank. So this one you compare with this one you compare with this one you compare with this one, and this one you compare with this one. And what changes you see is usually what's going to tell you what's happening, as long as you understand which one is polar and which one is non-polar. Okay, so first things you should understand is exactly what I was talking about. Salad dressing. Like dissolves like. This means that if you have something polar, something that you put into polar solvent will dissolve. If you have non-polar, and non-polar will dissolve. So I'm trying to think of something right off the top of my head. If you spill oil on your shirt and you put water, nothing's going to happen to it because oil and water do not go together. You will have to get something that's going to be able to mix with that oil to remove it, which means it's probably going to have a polar side and a non-polar side. Non-polar to interact and then polar to remove it off of your shirt. So here we have sodium chloride. Sodium chloride is something that if you ever put salt in water, you should notice that it dissolves. So that means that it's polar. It will dissolve. If you have oil is made up of nothing but but carbon and hydrogen bonds. A carbon and hydrogen bond is not, there's no polarity to it. If you remember the numbers that go with these, the electronegativity numbers, there's very little difference from them. That makes it non-polar. And so if you oil will interact with something else that is non-polar. So if you put something like carbon tetrachloride in oil, it will go straight into that non-polar side. Mama? So here is a perfect example of oil being added to water. This is like salad dressing where you shake it up. It will go into it and then realize, oh no, I'm not staying here. And it's going to go to which one is less dense is going to be on top and the denser one is on the bottom. So in this case, oil goes in and it will now sit on top. That's what we call hydrophobic. It's afraid of water. Hydrophilic is loves water. Now, so water is denser, they will sit on the bottom. That's what this picture, so this picture here is actually supposed to look like this. I think they could have did a better job or at least get a picture of it, but this is actually what this looks like here. So there's two distinct layers. You can count the distinct layers. When something dissolves, there should be no different layers in it. It should be one layer. But if something does not dissolve, then there should be two clear, distinct layers in it. So think of salad dressing. So sulfur, this is the first one you're going to be given. Think about, is it a metal, is it a non-metal? Will it go into, look on the picture, based on the picture, that's going to tell you which one it's going into. And that's going to tell you if it's polar or non-polar. Now, one of the things I want to point out here, this is solid. The reason why these are sitting at the bottom is because they're denser than the water. So regardless of polarity and non-polarity, they're just too heavy and they're going to sit at the bottom. But if they weren't, if they could match the density of the oil or the water, then they would stay floating. And then we have sodium chloride. So here again, you're going to compare which one is it. Pay attention to the little descriptions that all of these give you. It tells you where now below it what it is. And then you can see for yourself what these are. And then this is the last one. Again, they could have found a picture for it, but I found a picture for it. And now you can compare which one this goes into, which is actually pretty cool because you see which one this is interacting with and which one it does not. And the solid is only sitting at the bottom because it is too dense. And that is it. That's the lab itself. If you need part B is going to be a lot longer. You'll have to watch that video for when I go into more detail about it.